Okay, so in this video we'll be looking at ionic bonding. Now, ionic bonding is just one of the three types of bonds which hold all atoms together. So if you look around you, all the atoms around you are arranged in a certain way. They're held together by a type of bond, and ionic bonding is one of them. It's the glue which holds atoms together, and ionic bonding is specifically bonds together metals with non-metals. So if you see a metal like magnesium, potassium, or sodium, and it's bonded with a non-metal like chlorine or oxygen or bromine, then you know that ionic bonding is happening. Okay, so today we'll be going through each of the specification points, and there'll be some questions in between, and then you'll get the answers after, so you can self-correct. Okay, so you need to understand how ions are formed by either losing electrons or gaining electrons, and to understand this, you have to know that all atoms are trying to become stable. They all want a full outer shell of 8 or 2 if they're in the top period. So starting with lithium, we could to understand how lithium forms ions, we need to draw the electron configuration of lithium, and I'm going to draw the electron configuration. And we need a periodic table for this, so we need to look at the bottom number in the periodic table, and that tells us that we have 3 protons in the middle, and then therefore we're going to have 3 electrons on the outside. And following the 2A8 rule, only 2 electrons can fit in the first shell, then we have to fill up the next shell. Okay, so this is lithium's electronic configuration. Now, it is trying to lose. It wants to lose this outer electron because it's easier. It's easier to lose this one outer electron than to gain 7 more from a different atom. It's a lot easier to just lose that one. So lithium is very reactive. It likes to lose its one electron on the outer shell, and when it does that, it becomes, we still have 3 protons in the middle, but now we have only 2 electrons. Because we only have 2 electrons, if we have 3 positives, and then now we only have 2 negatives. So overall, we're actually at positive overall. So we've got 1 more positive than we do negative. So the overall charge on this atom is now positive because there's 1 more proton than there are electrons. Okay, then let's go to fluorine. So fluorine, again, we look at the bottom number of fluorine and we see that there are 9 protons, and if we draw out the electron configuration of fluorine, there's 9. Then it will look like this. You have 9 protons and then 9 electrons around the outer shell. It has 2 in the first shell, and then the remaining 7 are on the outer shell. Now, when it reacts, it prefers to gain an electron. It's easier to gain an electron from another atom than it is to lose 7 electrons. So it gains another electron from another atom. In this case, it's going to be lithium. So it's lithium and fluorine that are going to be reacting in this case. So we have fluorine, and it gains another electron. So we have gains an electron from lithium, and now it has 1 more electron than it does protons. So you still have 9 protons because the proton number does not change. If it does, then you've got a different element. And then now we have 1 more electron. So therefore we have an overall charge of negative because we've got 1 less proton than we do electrons. Okay, so this is what happens when ions are formed. Now I want you to use the same principle. For magnesium and oxygen. Now, you can pause the video now and give yourself around 2 minutes. Okay, so you should have something like this. So you've got 12 protons in the middle for magnesium. Now it's going to have 2 in the outer shell, then 1, 2, 3, 4, 5, 6, 7, 8, so it's got 10, and then it would have lost its 2 on the outer shell. And because it's lost 2, we still have 12 protons, but now we've lost 2 electrons, and we're going to have only 10. So we've got two positives. You should have had something like that. Your oxygen, on the other hand, that's got it's 8 protons in the middle, the nucleus. However, let's just show those electrons are on different atoms or part of different atoms. You have 8 electrons, then you have 6 in its outer shell, then it likes to gain 2, therefore, from another atom. Therefore, it still has 8 protons, but now it has 10 electrons, and therefore has an overall charge of 2 negatives. You should have got that. Okay, so here are some of the ions that you need to remember, and with your positive ions, your positive atomic ions, your group 1, group 2 and group 3 atoms, they all form ions depending with a charge equivalent to the group number that they're in, and it's always positive. So all your metals are always positive on the left hand side because they have 1 or 2 or 3 electrons in their outer shell, so therefore it's easier to lose them. So your group 1 elements, they always form positive charges, positive ions. Your group 2 always form 2 positive, and group 3 always form 3 positive. Now the transition metals here, you'll just need to remember those. As for the molecular ions as well, so your molecular ions, your positive and negative molecular ions, which are your golden 5, you need to remember that out of your head. Your groups, your atoms, your negative atomic ions, however, you can work these ones out as well. So your group 7 elements, they have 7 electrons in their outer shell, therefore they like to gain an electron to become a negative ion. Your group 6 have 6 electrons in the outer shell, so these atoms like to gain 2 electrons to become 2 negative ions. Your group 5 follows a similar pattern, so 5 electrons in the outer shell, and they like to gain 3 to become 3 negative ions. So you can work these, you can work these ones out, so it's not too difficult. And then these ones you do have to remember, but the ones that you remember, you use them so frequently that you will probably start to remember them quicker than you think. So when you're working out the chemical symbols for compounds, I would recommend that you write the ion above it. Now, this is where this comes in handy, knowing the charge of ions. So your ammonium ion, this is one way of doing it. I'm aware that there are many different ways, but this is the way that I like to do it. So if you have ammonium, I always write the ammonium ion above it, and this is a molecular ion. So if we have any multiples of this in our compound, we need to times it by 2, so we'll see. And then carbonate is CO3 2 minus. And again, that's a molecular ion, so if we have any multiples, we need to put it in brackets. So all compounds are neutral, and that's something that you do need to remember. So if they're neutral, these charges must balance out, so we must have the right ratio to make our compound neutral. So your NH4, that's one positive, and then your CO3 2 minus, that's 2 negative. So you're going to need 2 of your ammoniums. You're going to need to times this by 2. So your compound, your chemical formula is going to be NH4. We're going to have to put this whole molecule in brackets because it is a molecule that we need 2 of, so we need to times that by 2. That's CO3. Sorry, we don't include the charges in the chemical formula in the compound. So this is the formula for ammonium carbonate. So working out the formula for iron 3 nitrate, we know that iron 3, this Roman numeral here tells us that it's not iron 2 plus, it's iron 3 plus. Then your nitrate is NO3 minus, and if we're looking at the charges, we're going to need 3 nitrates to balance, to make our compound neutral, to have the right ratio. So we have 1 iron And because NO3 is a molecule, we need to put that in brackets because we need 3 of the whole molecule. And it's going to be NFNO3 brackets 3. Okay. So your aluminium oxide, again, same thing we do here. Al3. Oh, sorry. Aluminium's in group 3, so it's going to form 3 plus ions. Oxygen is in group 6, so it's going to form 2 minus ions. And then we need to look for a common multiple here to make our compound neutral. And our common multiple is 6. So to get aluminium's charge to 6, we need to times it by 2. To get oxygen's charge to 6, we need to times it by 3. So that's the common multiple there, 6. Okay. So your aluminium, we're going to have Al2O3. That is our chemical formula of aluminium oxide. Okay, and that's how you work out chemical formulas. Now there's going to be some practice on the next page. Okay, here are some practice questions for you. Now, before you try this, I would say again use the same method I've used, unless you've got a different method which suits you better. I always write the ions. That would help. CO3 2 minus and C2 plus. Okay. Give yourself about 4 or 5 minutes or however long you need, and then replay the video after for the answers. Okay, so you should have got this for your answers. Now, if you didn't, just write the ion, the charge of the ion above it, and just see where you went wrong. Okay, see where you went wrong. Okay, now you do need these brackets as well. Okay, so ensure that you've got the brackets. They're very important for the molecule. So you should have brackets around molecular ions if you have a multiple of them. Okay, if there's no multiple, then you don't need the brackets. So you don't need brackets here. Okay, no brackets needed. Okay, you need to be very confident in drawing dot and cross diagrams. And if you're not, I would say then the first step is to draw out the atoms first. So with aluminium oxide, I think it's always best to draw out the electron configuration of the atom. And you only need to draw out the outside. Aluminium's in group 3, so it has 3 electrons in its outer shell. Oxygen is in group 6, therefore it has 6 electrons in its outer shell. Very easy. So these are your atoms, and they turn to ions. So then drawing the dot cross diagram for the ionic compound of aluminium oxide, you then need to draw these atoms as ions. And you can see what happens. Remember what we said, that all atoms like to have a stable outer shell, and that stable outer shell needs to be full. So it needs to either be it either needs to be empty or full. So your aluminium will lose these 3 electrons to get a full outer shell, or to reveal its outer shell underneath, and your oxygen will gain 2 electrons to get a full outer shell. So if we do our oxygen, so oxygen looks like this. It will gain 2 electrons from the aluminium. Now that will have a 2 negative charge because it's just gained 2 negative electrons. Your aluminium, on the other hand, has just lost 3 electrons. And that's now become a 3 positive because now it has 3 more protons than it does electrons. Okay, so here's your ionic bonding. Now the only thing you now need to do is to also include the correct multiples and the correct ratios. So your aluminium, you're going to, for every 2 aluminium atoms, you're going to have 3 oxygen atoms, okay, reacting. So your compound is going to be, your chemical formula is going to be Al2O3. Okay, now these multiples are important. You get a mark for the multiples, you'll get a mark for your charges, and then you'll get a mark for the correct the correct number of electrons around the outer shell. Okay, can you give these 2 a try, please? Magnesium fluoride and potassium bromide. You may pause the video now. Okay, so you should have got these for both of your answers. Okay, again we've included the correct multiples. Okay, so here, so at the bottom here, fluorine has there's two fluorine atoms. You don't have to draw out a whole nother fluorine atom. You can, this person in here could have just put _2 next to fluorine, okay, it doesn't matter. But the correct multiples is a mark. Sometimes in an exam, it may ask you to describe ionic bonding in terms of the ions involved and the electrons involved. So here is a practice paper question, and it says here to gain full marks you must use the word atom, electron and ion in your description of what happens when magnesium reacts with iodide to form magnesium iodide. Okay, so I'll give you 4 minutes because there's 4 marks to answer this question. Then we'll go over the answers. It's a very easy one. You can bullet point here. Okay, go. Okay, so you should have got something like this. So atoms. So first we could talk about atoms. So which atoms are involved? Magnesium. So the magnesium atom loses 2 electrons to become an Mg2 plus ion. Okay, so we've used the word atom, electron and ion. Let's do the same for iodine. So iodine atom gains. Iodine atom gains an electron to become an iodide ion. Okay, so an iodine atom gains an electron to become an iodine ion, and so we can say here, because there are 2 iodine atoms involved, you can say 2 iodine atoms gain an electron each to become an iodide ions. Okay, that will get you all 4 marks there. Here's a practice paper question for you to try. In an exam, you'll get a maximum of 3 minutes to complete this. So I suggest you give yourself the same, and then we'll check the answers after so you can self-correct. Okay, so you should have got something like this. Now you can give yourself marks depending on this scheme here. Did you include the charges? So did you get the right charges? 3 minus and plus. Do you have the correct number of electrons in the outer shell? So 8 for nitrogen, 2 for lithium. So you do have to be careful because lithium is in the first period. So it does only have 2 or need 2 electrons, and in its outer shell. And then multiples. Have you got the correct multiples? So you need 3 of lithium. So 3 lithiums here. Okay, so we'll go through your last 2 specification points. And your second to last one is 1.42. Understand why compounds with giant ionic lattices have high melting and boiling points. Now this is very easy and a question that comes up a lot actually in exams, but it's always answered the same. So you have many strong ionic bonds which require a lot of energy to overcome. So you need to remember that in this structure, in this ionic structure here, these are 2 different models, just to help you understand what's actually happening and how those molecules have arranged themselves in this regular repeating pattern, which is called a lattice. In this pattern here, there's millions and millions and millions and millions and millions of atoms in this solid, and for you to turn it into a liquid, you actually have to break every single one of those bonds to turn it into a liquid. And you can imagine how much energy that requires if you're breaking all these bonds, and they're all quite strong. Okay, so that's why salt has a high melting point. You have to break every single bond between the sodium and chloride ions. Okay, your second specification point is 1.43, last one, and know that ionic compounds do not conduct electricity when solid, but do conduct electricity when molten and in aqueous. Now again, this is just easy. It's very easy. So when your ionic compound is solid, the ions are fixed. They can vibrate, but they're fixed. They can't move. Okay, so they can't conduct. Okay, for you to conduct the electricity, you need to have charge which can move. Your charge needs to be mobile. But then when your ions are in a molten state, when they've been heated or melted, and that requires a lot of energy, remember, or they're dissolved in water, which actually doesn't require that much energy. Your water part, it doesn't require as much energy there. Then it can conduct. So ions are fixed when in solid state, but ions are mobile in aqueous and liquid state. So they can conduct, and your light bulb will turn on if you connect them to a circuit, but they won't if it's solid. Okay, here is a summary sheet of ionic bonding. There's also a bit of covalent bonding here as well as a summary and a comparison. There's 8 questions. Give yourself, I'll say, around 15 to 20 minutes, depending on how long you need, and then you can correct your answers after. So you can pause the video now. Okay, then you should have got these answers here. Now, I just want you to note that this is one thing that a lot of students get wrong, that when you're talking about covalent, simple covalent structures, that is your chlorine here, so simple covalent structures, when there are molecules of chlorine, then molecules of a covalent molecule, then there are weak intermolecular forces between the molecules. Except for in graphite, but there are weak intermolecular forces between the molecules. Okay, so that requires a little energy to overcome, so they have low melting points. All covalent molecules, they have low melting points. Therefore, most of them are gases at room temperature. You've got a few exceptions like water, which is a gas, but most of them is a liquid, sorry, but most of them do have low melting points. But you need to be careful that you know what type of forces are being broken when you change from a solid to a liquid or a liquid to a gas, and depending on what type of structure is involved. If you're looking at simple molecular, it's these intermolecular forces which are being broken. If you're looking at ionic bonding, then ionic bonding, it's these bonds here. It's these strong ionic bonds which are being broken. If you're talking about giant covalent, then you are breaking covalent bonds. Okay, so you need to know what type of bonds you're breaking, and that will tell you whether the melting point is high or low, whether you need to put in a lot of energy to break them or not.